Now, Mike, I don't want you to be muted, please. And really, I wouldn't like Roger to be, or Bill, or John, because there's no feedback, audience feedback in these things, you know. And so I can't tell when people are shuffling or feeling uncomfortable or they can't hear. And it would be excellent to get some feedback from you, some audio feedback, if you have any, on behalf, as it were, of the audience. I've moved to the next slide by accident. You can see that from the title that my talk will be about what probably for most of you is a rather prosaic subject, which is high power in electrical engineering. The sort of things that use high power DC are electric trains, cranes, and so on. Nowadays we have solar power, that's high power DC. Electric cars will have high power, but most of you probably don't give a thought to whether they're DC or AC, but you will have been familiar with things which are DC at low power levels. And over the years, you'll have used the telephone, the old-fashioned TV, maybe had a toy train set like I did, modern mobile phone. All these are low-power DC users. But interestingly, things like the television would have had about 2,000 volts of DC to operate it. I'm not concerned with them. Actually, there's no problem getting DC at low power. The problems are at high power. Now, it seemed not unreasonable, given the variety of backgrounds of the audience, that before we get into something, I better try and explain what DC and AC mean, because they're used very widely, and I believe they're frequently not understood. So let's look at a couple of examples. And these slides with the green background, it means this is the introductory bit saying what DC and AC are. Direct current, DC, it means basically what it says, that it's direct, and the word direct means constant in magnitude and direction. So here the battery pushes out current from its positive terminal, shown by the red arrow, through the wire, through the lamp, and back to the battery. And that's a constant current. It doesn't vary with time. Well, of course, not until the battery runs down. So that's a positive current. And if we were to draw a graph of it as against time, obviously it would be a constant. And the reason I'm introducing graphs is we'll need it when we come to alternating current. But before we do that, let's have a look at what happens if we put the battery the other way. Now, for a lamp, it doesn't make any difference which way you connect the battery, but the current will always flow out of the positive terminal. And so it will be going the opposite way along the wires and through the lamp. And the convention is that we would call that a negative current. So when we draw the graph of that one, obviously we get a minus. I've chosen it to be 5 amps. We get a minus. Steady current. Notice it doesn't vary with time. Things are very different when we come to alternating current. The name's a bit of a giveaway, really, isn't it? An alternating current has a magnitude and a direction, both of which vary with time. I've drawn a graph here showing an alternating current that goes up to 5 amps, then back to 0, then changes direction and goes to minus 5 amps, and so on. Now, it doesn't have to be, as I've shown here, a sinusoid. It could be a triangle, square, anything that periodically reverses direction is an alternating current. But we will be, I think, more or less exclusively, until the end of the talk, we'll be dealing with sinusoidal quantities. Something worth mentioning is that if you have a steady DC current, you need a steady voltage to drive it around the circuit. And somewhat confusingly, we call that a DC voltage, which is linguistically a bit crazy. And how can you have a direct current voltage? But we would call a voltage of a battery would be called a DC voltage, 1.5 volts DC. And similarly with alternating current, we need an alternating voltage to send the current around the circuit. So there's a bit of an introduction. I hope for those of you that had the vaguest of ideas, it may be slightly less vague now. And what I'll do now is say what's in the talk, which has 5 sections to it. So I'll flag each section as we come to it. And those of you that get really bored, of course, can go and make a cup of tea or leave the meeting altogether, which is something you can't do without embarrassment in a meeting in the Clark Foley. So there's an advantage there. And you'll be able to think, well, I managed to stay until the 3rd or the 4th or whatever. Anyway, there are 5 sections. I'm going to briefly touch on the battle that took place at the end of the 19th century between AC and DC systems, which eventually were settled in favour of AC. I'm going to look at why AC is dominant, and then I'll look at how AC was converted to DC for many applications that needed it in the power levels, high power, for about the first 70 years. And then things changed very much, and we moved into the era of power electronics, which allows us to do things much more efficiently and rapidly. So there'll be a step change there in the nature of the technology. But again, it's something that the man in the street would never have noticed. And finally, we are now able to convert back from DC to AC, and you may wonder why that is, and I'll try and illustrate that. Going on the first section, the current wars, there was a film last year, I don't know if any of you saw it, and that dramatized the battle between AC and DC. And why did electricity suddenly take off at the end of the 19th century? It was primarily because of the electric light, the ability to have to supersede candles and gas lights and so on was rapidly seen by entrepreneurs as a money-making venture. So real spur to the development of electrical generation in power quantities was the electric light bulb. And here's some of the other pretty looking ones from that period. So we get into part 1, the so-called current wars. Well, I'd never heard the term current wars until I saw the film last year, which I thought was quite a dramatic title, although enigmatic as well. A lot of people wondered what it was about. It told the story of essentially the fight between DC proponents headed by Thomas Edison and AC favoured by Tesla and backed by Westinghouse. Now, Edison was an entrepreneur and also able to attract funds, whereas Tesla was more of a quiet backroom. No, he wasn't quiet, but he needed a financier, and he got Westinghouse to back his scheme. But let's have a look what Edison's system looked like. This was one of the earliest setups in London and New York. The generator is the, I don't know if I can use the pointer, I'll try. Yes, this is the generator here on the right, and these are the coils that produce the magnetic field. And that's, what was that, for 1500 lights, 1882. The AC system, well, that was, Westinghouse was the financier and the industrialist who backed Tesla, and ultimately, of course, won. And there is a picture of his generation systems. I've just realized that I'm going to have a job keeping time, because on my presentation there's a timer which tells me how long the talk's been on. But before we started the talk, long before, Mike asked me, should we just have a practice, see if you can screen share? And we tried it. It's been timing since then. So I'm in 48 minutes into my talk, and I don't know when I actually started. So Mike again, Roger, Bill, just shout up, unmute and shout up if I'm going on far too long, please.
Going far too long.
What?
Nothing. Nothing.
Okay.
You've had about 10 minutes, quarter of an hour.
Okay, so I'll knock about, right. Thank you very much for that, Mike. Right, I can do the maths. Let's look at the pros and cons of the two systems. You can see that the AC system on the right is efficient for transmission over large distances and short distances. It's okay for lighting, it can produce fixed speed motors. The only thing it couldn't do was provide a cheap and effective variable speed motor. Conversely, the DC system was good for lighting and fixed speed and variable speed motors, but no good at all for efficient transmission. Now, it says over hundreds of miles. Actually, it was even within cities. It was not efficient. And the reason for that is that with AC, we can use transformers to change the voltage from what's generated to a much higher level to transmit it. Now, you may say, well, why is that? Well, I mean, what advantage is that? Well, you have to look at what power is, and power is voltage times current, or watts is volts times amps. So imagine we've got a fixed amount of power that we want to transmit. You can look at the fact that that's a product of voltage and current and realize quite quickly that the more volts you have, the less current, the fewer amperes, which basically means thinner wires, because carrying current through conductors is much like carrying fluids through pipes. If you've got a high flow rate, you need a fatter pipe. If you've got more amps, you need a thicker wire. So without wanting to tread on Mike's toes, because he's going into this in one of his talks, I'll just show you briefly how the power system looks typically, until recently anyway. The power station on the left produced electricity at maybe 27,000 volts. That was transformed up to perhaps 400,000 for remote transmission across the country from the generator to the consumer, where of course at 400,000 volts it would be unsatisfactory in the home, so it's transformed down to lower voltages, and you typically are up here getting a 230, 240, 250 volts. And I've just shown a couple of pictures of transformers. These are large things, but they can be very large, they can be small, but they're very efficient, static, no moving parts, typically 99.8% efficient in the large sizes. So AC, you can do that and you get the economy because we're transmitting the power long distances. We need low current, we only need low current, and therefore we don't need a lot of copper conductor. And to put that into context, let's have a look at the comparison of the volume of copper conductor that you would need to transmit a fixed amount of power. If we were to do it, we have to use. We don't, we go up to a much higher voltage, like 400,000 volts. And as current. We need fancier insulation, but it's definitely a good idea to save copper. If we look at the cost of the wasted energy, because of course the wires do get warm and they radiate some power, and the birds sit on the transmission line and get their feet warmed. But if we look at the cost of wasted energy per minute, if we were at 250 volts, it comes out at £16. If we do it at 400,000 volts, it comes out at a penny. So it's pretty obvious why AC1, we can transmit at high voltage, which brings massive benefits. If we look at dominance of AC, I'm actually going to look at how AC is produced, because that's behind the dominance of AC and the fact that we use transformers. Really, this all goes back to Michael Faraday, a remarkable fellow, started life as a lab assistant to Humphrey Davy. And probably his most famous result was the law of electromagnetic induction, and where he showed that you could get voltage produced in a coil of wire, which was proportional to the rate of change of the magnetic field through the coil. It sounds a bit complicated, so let's see what it means. Here's a bar magnet, and those lines, you'll perhaps remember doing them with iron filings. They're an entirely hypothetical concept, but they're useful for us coming to grips with the difficult ideas that surround distributed quantities, in this case a magnetic field. If we put the magnet next to a coil, we just take the magnet, stick it next to a coil and see what voltage is produced. Well, we don't produce any. And that's not a surprise, because although the magnetic field is through the coil, it's not changing because nothing is altering. Now at this point, when I prepared this talk, I thought we'd be in the Clark Foley. And so I had an animation that showed like that where the coil went round. When you try to run animations in Zoom, the vagaries and limited bandwidth means that it's very clunky. So I've had to take all that out. So I ask you now to imagine in the next few shots that the magnet is rotating at a uniform speed and that we are going to take a snapshot of it at various instants. So the first one would be there. See the arrow showing it going round? You've got to imagine it's whirling round. It's back to the old days before we could have movies and things. So there's a voltage produced when it's in that position, provided it's moving. Go further on. Oh, the voltage has got even bigger. And funnily enough, those of you who remember the field pattern realise there isn't any field through the coil now because it's pointing up and down instead of across. But the rate of change is very high at that point, so we get a large positive voltage. We go a bit further, voltage reduces, 0. And notice that the voltage is now in the opposite polarity. It's alternating. So each revolution takes the voltage through a complete cycle. I've plotted the voltage at various instants on this slide. And you can see that in one revolution, you get a positive set and then a negative set. And so it goes on. Well, we don't normally plot them individually. Of course, we would normally just use a graph. Now, if you think back to Faraday's law, he said that the rate of change was what determined the voltage. So that means if we go faster, twice as fast, we're going to get more volts. And what's more, we'll get a complete cycle in only half the time. So we get that. You can see from this, if you think back to those of you that know that the UK frequency is 50 Hertz, which when I was a lad was called 50 cycles per second. So in the UK, we're generating at 50 cycles per second. So the magnet has to go around 50 times a second, which is 3,000 revs a minute. And most of the generators in most of our power stations go round at 3,000 revs per minute. And that has an important implication for lighting, as we'll see in a minute. They don't usually, when generating the AC, just have one coil. They have 3, and each one is called a phase. And you can see them here. And of course, they're identical coils, so you get 3 different voltages for each coil, but they're the same amplitude, the same frequency, and they're a third of a cycle apart. And when my wife Jean saw me doing this, she said, well, you may think you're an electrical engineer, but you might be a wallpaper board designer as well. So I'm putting that up to remind you that's why on the towers that stride across the countryside, and some look at them and say how majestic they are, and others say, oh my goodness, what an eyesore. But there are normally three arms to support each phase. Those who went to Drax wouldn't have seen inside the generator, but if we could have taken the time off, the cover off, it would look something like that. It doesn't look anything like my diagrammatic coil, but believe me, there are sets of coils there. It's about 20 feet long, that hole up the middle. That's where the magnet gets put, and the coils, there are 3 sets. You can't tell, but I've coloured them in. So we've got the red set, the blue set, and the green set, and they are generating the 3 lots of the magnet is a magnet, not a permanent magnet. There it is. To give you some idea of the scale, it's an electromagnet and it sits up the middle. Well, how do DC and AC compare when we come to use them? Well, if we look back to the battery, at this point, had we been a live audience, I would say, what do you think will happen when the switch is closed? And I would have hoped you'd all have said, well, the lamp will light up. which would have assured me that some of you anyway were still with me. Now, why does the lamp light up? What is it that causes it to light up? Well, it's the current that flows when we close the switch. In this case, I've put some numbers on because we'll use those in a minute. I've said I've got a 10-volt battery, and I've said that 2.5 amps is going to flow clockwise in this case through the lamp. Supposing we reverse the battery, will it work? Well, of course it will, but the current will flow the opposite way. So let's assume that we've left it on and we want to know what the power is. Excuse me a minute, because I've just got to manipulate my screen because I have an image of the hosts which is blocking my view of what I'm supposed to be talking about. So I'll put it down there. No, up there. I'm sorry, you don't know what I'm doing, but let's look at the graph showing what's going on here. The current is constant, 2.5 amps. The voltage is constant, 10 volts. The power, which is the watts times the volts times the amps, is therefore 25 volts. 25 watts, I do beg your pardon. And it's constant, it doesn't vary at all. So the power generated inside the lamp is absolutely invariant with time. Now suppose we replace the DC voltage by an AC voltage. Will it still work? Well, of course it will. We know it does. That's what we have at home. But now we have a voltage which is going up and down, and what's more, it's changing direction. So when the voltage goes up with a lamp, the current goes up too. In fact, the one is proportional to the other. So when we draw a graph of what's going on, we start with the voltage which goes up and down. And the sharp-witted amongst you will say, well, why has he chosen 14.14 volts for this? Well, that'll become obvious in a minute. There's no magic to it. The truth is, I want it to be operating so that the light looks no different to you and me than it did when it was with DC. So in this case, with that particular lamp, the current will follow the voltage up and down and go up to 3.5 amps. Now we want to look at the power. So let's see what power is. Well, it's volts times amps. So we've got to multiply it every instant along that graph, left to right. We've got to multiply the amplitude of the volts and the current. When we do that, to get the watts, which is the volts times an amps, we get this. Clearly, there are periods where both voltage and current are zero, so the power is zero. And there are periods where voltage and current are maximum, so the power is maximum. So inside the lamp bulb, some of the time we're drawing 50 watts from Yorkshire Electricity, sometimes zero. Now, it's not much point bringing them up and saying, well, I'm not drawing any current for every 100th of a second. I don't draw any power. You don't need to send me a bill, because they'll turn around and say, yes, we do. You're drawing 50 watts. Obviously, what really matters is what's the average. And in this case, of course, the average power is 25 watts, exactly the same as it was before. Now, if you're thinking, well, does that mean that inside the bulb, the filament is alternating between 50 watts and zero, so it's glowing brightly and less brightly? The answer is yes. It's flickering, but it's not. If you look at the times involved, we're on a 50 cycles per second supply. So that peak going up to 50 and back to zero is 1/100th of a second. And our brain and our eye system is not sensitive to it's beyond the frequency response of our eyes. I mentioned earlier about the generators having to go at 3000 RPM to produce 50 hertz. Well, one of the reasons that settled the frequency originally when the business started up was that the incandescent lamps at the time, if you had a frequency below about 30 hertz, the pulsations were perceptible. And it was very irritating. So the decision was inevitable. We're going to have to drive the generators around faster to stop people getting flickery view. So it's too fast to notice. So lighting and heating is very similar. They're okay for DC or AC. But what about when we want things for industrial powers, and in particular variable speed motors to drive? How do they compare? Well, if we look at the world use of electrical energy, about 40% or so is motors, heat and light, etc., and the others. And of those, of motors, the vast majority is used in fixed speed AC motors called induction motors, which most people in a domestic environment will never encounter in their lives. They're not used in your home, or very rarely. That's fixed speed. But for variable speed, there are two types. You can see here, historically, from the time that power generation became widespread, for the best part of the first 90 years, the only effective variable speed motor was a DC one. There were a few AC ones, as you can see there. When power electronics came in the 1960s, 70s, the things gradually changed, and now the vast majority of variable speed electric We'll first look at why DC motors were so important. They're very versatile, and we'll start by a little bit about them. They're versatile, but they're expensive because they're quite difficult to construct. And I'm showing you a DC motor there, and so let's look at a DC generator. Well, the perceptive amongst you will say, well, I can't see any difference between them. Well done you. There isn't. A motor can act as a generator and a generator as a motor. It's just a machine. If you ask it to produce mechanical output power at the shaft, it will draw mechanical power into it, for example, by connecting it to a diesel or a petrol engine. It will produce electricity. You don't need to change anything, rewire it or anything. Incidentally, the little thing at the top, the little motors that are sitting up here, they're just cooling motors. They are in fact AC motors. If we looked inside the DC motor, here's a big one. They make them in 2 bits because they're awkward to ship around. It's got a stationary bit, which is basically a set of electromagnets, and they don't have much power. They don't need a lot of power. They just make it work. They're the catalysts, if you like. The business end of the DC machine is the rotor bit with coils that you can't see and a commutator. Each coil is connected to a copper segment on there. And this is an expensive thing to make, as you can imagine from the look of that. In this kind of motor, the power actually is produced in the rotor, and so the rotor carries heavy currents and quite large voltages. And how do they get there, given it's going round? Well, they're fed in through things called carbon brushes that rest on that ring of copper segments. You can't see very well there. Let's have a look at a carbon brush. Oh, just before I do that, it has to be admitted that inside the rotor of this so-called DC machine, steady current, all the coils actually are carrying AC current. But that commutator, that thing at the end there, copper segments on a cylindrical former, is in fact a mechanical rectifier. And it rectifies the AC and produces lovely smooth DC for the outside world. But it's frequently not realized that all machines actually are AC, but from the outside world point of view, the current that is fed in and the voltages are DC. I mentioned brushes. Here's a quick look at a brush, carbon brush. You might have these things in your food mixer or your electric drill. And it always puzzled me why they were called brushes. So I looked into it, and their predecessors were like this. Early DC motors had brushes made from bundles of wire, like a witch's broom. And they, of course, scratched the commutator and made grooves in it. So the graphite or carbon brush took over. Now, I mentioned why the DC machine is very versatile. Well, one of the things that's good about it, if you want it to go the opposite way around, you just reverse the brush, the polarity of the supply. So in the top one, it's getting a positive voltage and it runs clockwise. Negative voltage, it goes anti-clockwise. The speed, well, again, it's very simple. The speed is proportional to the voltage across the brushes. So if we have one V applied, it goes at 200 revs a minute, maybe. Double it, it goes at 400. Well, that says, well, this is a useful motor for getting variable speeds for industry, but how do we get DC when the power system is AC? How do we get a variable voltage DC from a fixed AC? And that's been the challenge throughout the 20th century. Well, in the high power range, we really had three systems. First of all, up until the Second World War, really, we had what's called a motor generator. I'll tell you a bit about that. Then we had mercury arc rectifiers, very extraordinary device. But from then on, we had solid state thyristor, which is the modern way of doing things. Let's just briefly see what happens when we use the DC machine as a generator. You don't need to take all of this in. Just imagine we're running at a fixed speed. It's driven by another motor or a diesel or whatever, steam engine. And it's driven at 1,000 revs per minute. And when we increase the current in those little field coils, proportional. So we have a way of getting a very, we need something to drive it. And the way we did that was called a motor generator set. And there it is in the green dotted line. There was a fixed speed AC motor directly connected to the industrial three-phase supply. And that ran at a fixed speed and drove a DC generator. And that in turn produced a voltage that depended on how much current we fed into its field, which went out to the DC motor whose speed had to be controlled out on the workplace. Now, the motor generator set could be in a plant room remote from the motor out on the crane or wherever it was. But notice that in order to drive, let's say, a 1,000 kilowatt motor, you needed the 1,000 kilowatt motor, an identical 1,000 kilowatt machine used as a generator, and another slightly different but 1,000 kilowatt rated motor to drive the generator. So no wonder there were lots of companies in Britain making electrical machinery, because to get one, you had to have three. Very good business. Here's what they looked like. These are MG sets in the plant room. I must admit, we're first in industry. I wondered what on earth they were. They didn't seem much point in one driving another round, but they were producing variable voltages to go out to the work machine out on the plant. Here's a bigger one, much bigger set. My introduction to this came when I was a student apprentice and working on the new steel mill down in South Wales, installing the new equipment. And on my first day, I was taken to the room where the motor generator sets were early in the morning, and was shown them and told, well, you can start the motor generator set because we'll be testing some machines soon. So I want you to go over to that cubicle and press the green button and start it. And I did that, and I have the most vivid recollection how incredibly scary the noise of this thing starting was. And feeling, well, is it ever going to stop? And I thought, well, it'd be nice if I had a recording of one. Well, I couldn't find one, but I've got one. I've got a recording of a little one. I don't know if this will work. This is a much smaller machine, but that's a 160 kilowatt. The one I was starting was a 10 megawatt, so that's 10,000 kilowatts. But I'm hoping the audio will allow you to get some sense of my fear almost of when on earth is this thing going to stop. I think we'll stop there. I don't know if you could hear that, but you can imagine how frightening it was for me.
Austin, we could
Well,
hear
now if we
it,
look
but it
at,
was very frightening.
yes. Oh, good, good, you could hear it. Thank you for that, Roger. Let's look at different types of ways of converting AC to DC that didn't involve three electrical machines. Those are rectifiers, devices that conduct electricity in one direction only. I've got 5 here, but I'm going to disregard the first 2 because they are very small power ones. You'll have seen valves and rectifiers in a battery charger, maybe selenium, but at the power levels that I'm interested in, we really had only 3, which was the mercury arc, the silicon diode, and the thyristor. These all went up to quite large powers. The mercury arc rectifier, here's a glass type of mercury arc rectifier. A most extraordinary thing. Again, my first encounter with these, I could hardly believe how, I don't know, frightening it was. You're not supposed to look at it because the radiation is bad for your eyes. Basically, if you have a pool of around it, you connect the mercury as a cathode, it will conduct from the anode to the cathode, but not the other way around. So it can rectify or limit the current. If you connect it to AC, it will only conduct on the positive half cycles. And these things had been used for quite a number of years in static installations. But when British Rail decided to electrify the system, the company I was at, which was GEC, I was a student apprentice, and they put these rectifiers in these locos. Now, these were brand new in 1960 on the west with a transformer inside to drop it down, and then rectify the AC to drive the motors, the traction motors. And they use mercury arc rectifiers, which are a pool of mercury in the bottom of a tank. And you can imagine when a loco is bucking and weaving around at high speed, the mercury slops all over the place. And if it slops too much, it causes a short circuit with an almighty bang, which puts the thing out of commission. So the GC locos were towed. They were no good. They kept packing up. And they towed them to Whitton Goods Yard, which is where I had my second year university vacation experience working on rectifying the problem. Sorry, no pun intended, putting right the problems. The rectifiers had to be taken out and baffles put in to stop the mercury slopping around. They moved them to this place called Whitton, which is in Birmingham, and that's where the GEC factory was, and that's where I was allocated for the summer. And it turned out because I was quite a good welder by then, I'd been through all the student apprenticeship training, and I was a pretty good welder, and there was a lot of structural welding to do, and I loved doing it. And the fitters, once they got over the fact, oh, this is university twerp, he won't be any use, they decided, well, yeah, you can be trusted to do the job. And I was left with minimum supervision, welding for most of the day, while they played in the cabin, played cards and drank tea. And that was fine, I was loving it. But then the shop steward came over from the factory to the railway goods yard, and he had his facts, and he said, a fitter is worth £22 a week, and a student apprentice is only worth 6. So unless this student is stopped from working, I'll be calling a strike. So I had to stop work, which was very disappointing. Anyway, mercury arc rectifiers really were not very good for railway use. And indeed, they were rapidly superseded in all applications by solid state rectifying devices. And here are some pictures of some diodes. I'll tell you in a minute what a diode is. The 1 milliamp ones are on the left. There's a bandolier of them. And the one on the right is a 2,200 amp with a 50 pence piece for comparison. And these do the same job as the mercury arc rectifier. Here's a symbol for a diode. It's simply, the black arrow shows the direction of current flow. It can flow from right to left, but not from left to right. And catch the people who are asleep, because I put a circuit there to drive a motor, And if you remember from earlier, the current has to come out of the positive terminal and flow along the top wire through the switch to the motor. And I put the diode in that way, and I was going to say, what do you think will happen? And hope very much that people would say nothing, because you've just told us that the diode can only conduct current from the right to the left, the direction of the arrow. So when we close the switch, it wouldn't work. The diode is what's called reverse bias, so no current. However, if we put the diode that way round and close the switch, the motor will go. And the purpose of this diagram is to show that the diode doesn't really waste much of the voltage that comes out of the battery. We've got 10 volts there. I've said that all of it gets to the motor. Well, it doesn't quite, but it's more or less as shown there. Now, the value of the diode comes when we want to supply the motor, which is a DC motor, from AC. So let's see what happens then. We replace the battery by an AC source, one that goes up and down, positive and negative. Well, it will only conduct current from the source on the left to the motor on the right when the voltage is positive. As soon as it goes negative, it won't conduct. So what gets to the motor is the positive half cycles. So that's one pulse every 50th of a second. It's not very good DC, is it? It isn't steady current, but it's in the same direction. And that's what counts as far as the motor's concerned. So it's not very good DC I'm giving it, but it's unidirectional and the motor runs okay. Now, looking at just a little bit more detail, you can see that just as with the lamp, we saw that it was the average that mattered. Well, likewise here, the DC voltage shown by the dotted line is the average, the mathematical average of that VM, the motor voltage. So it can't respond to the 50 hertz pulses. You may say, well, the speed is going, the voltage is going from 0 and then up to a maximum down. Well, surely the motor will be up to speed, then it'll stop again. No, the inertia of the motor prevents it from responding to the 50 hertz pulses, just as the filament of the lamp smoothed out the pulses it was getting. So the motor works reasonably well, though, as you can see, it's only benefiting from half of the electricity supply that's available. So we have another trick up our sleeve. If we use 4 diodes connected like that, we can allow the current to flow the same way through the motor on both half cycles. Now, I chose to show this by going with batteries because it's a bit easier. And we'll put the AC supply on afterwards. With the battery connected one way up, positive, I've shown with the red line that current flows into the top of the motor, out of the bottom and back to the battery. So the motor is going round clockwise. When we switch the battery the other way up, the battery to send the current now out of the bottom, the top of the motor, so the motor still wants to go clockwise. So that means when we change the polarity of the supply on the left, it doesn't change the polarity of the supply through the motor. So if we replace the up and down batteries by AC, then we get both half cycles exploited. And that's called a full wave rectifier. So the motor gets twice what it was getting before. And again, the speed of the motor is proportional to the voltage, but the inertia prevents it from accelerating and decelerating within such a short time. It smooths it out, and the speed depends on the average voltage. If you want one of these rectifiers, it just looks like that. The diodes are all potted. The whole thing is solid state. 2 of the terminals you put AC in, and out of the others comes DC. Only we now know it's rectified DC, not smooth, but nevertheless unidirectional. And if we had a 3-phase supply like they have in industry, oh, it's wonderful, because we've got 3 lots of voltage to capitalize on, look, and we only need 2 more diodes. We've got 6 diodes now in our converter at the top, and we're getting a pulse every 300th of a second. And really, that's pretty damn good quality DC that we're getting there. So that's remarkable that we can get such nice, smooth waveforms out of sine waves. So, part 4, power electronics. Well, you'll all be familiar with the enormous impact of semiconductors in the electronic area, computers and mobile phones and so on. Well, a similar revolution took place in the heavy power side of things. And interestingly, one of the locos I worked on and did welding in, I think there were 6 of them, here's one of them. It was rebuilt with the modern technique of thyristors, which I'm going to tell you about in a moment. And it emerges looking a bit different. And it's now in the museum. I'll show you in a minute. That tank of slopping around mercury is replaced by solid state devices called thyristors, which, as I say, I'll tell you about in a moment. Here's one. Oh, that's a diode. There's a thyristor. I put that's N12. It won't mean much to most of you. It's a 1/2-inch thread. I'm just putting a scale on the diagram, but it's much smaller than the mercury arc rectifier, and indeed a much more efficient, because the mercury arc rectifier arc wasted about 30 volts. These don't. I mentioned that the loco I worked on is now in the York Museum. There it is. Really makes you feel old when you've served your apprenticeship and then you end up seeing the stuff, taking your grandchildren around and saying, well, I worked on that when I were a nipper. Right, voltage control. We saw how we could get some us to do that. It's like a diode, but it's got a little terminal called a gate. And the gate's a good name for it because it's a diode which will conduct from right to left, but only when the gate's open. And you have to open the gate with a little bit of electronic pulse going in there, just a little squirt to set it free, as it were, and start conducting. So we've got, as it were, a diode that we can turn on and off at will. And the consequence of that is that we're able to have a circuit like this, with AC on the left, a thyristor rather than a diode at the top. And when we vary the gate, the time that we put the gate pulse in, we can vary the output. The output is shown by the black line at the bottom. And see that Greek alpha, that angle of delay, that is how I've waited. I didn't pulse it when the voltage would have been at 0. I waited a bit. So the waveform that's going out now is missing the first bit. So the average of it is less than it was before. Now the beauty of this is that the control signals to do that are very low power. They can come from, nowadays they come from a microprocessor. But the signal that it's controlling could be thousands of amps. And we can turn them on. We can't turn them off, that's another story. When we want to get smoother output, we would have 4, like we did with the diodes, and that allows us to control both half cycles. It's a full wave output, and you can see on the left with a delay of 45 degrees, you can see that the average voltage VDC is quite high. If we delay the firing until 135 degrees through the half cycle, we get much reduced output. So we've got a way of controlling the amplitude as well as rectifying it. That means we can feed this to a motor. The motor is very tolerant. As long as the voltage in the same direction, it's quite happy. And it's a very efficient process, which it has to be for power levels. They're very efficient devices because they closely approximate a switch. Either they're on or they're off. They're not in between. And you can see there that the voltage drop over when they're on is quite modest. Of course, if you started with an AC supply of only a few volts, then losing 1 or 2 is quite important. But if you start with 500 and lose 1, well, you're not too bothered. You will actually have had these things in your home if you've got a light dimmer. The light dimmer has 2 thyristors back to back, combined as it were. It's called a triac, and it allows the electricity waveform coming into your house, which is shown in this graph as green. That's the alternating voltage from the Yorkshire electricity. You can cut out parts of it depending where you set the gate pulses with your little twiddle knob. So your lamp gets the red waveform. We're back to lamps now, which are perfectly happy with AC. It's not rectifying, it's just throttling some of the each half cycle. So the lamp intensity clearly goes down when we use a triac. Well, we're getting to the end. As I say, I was a bit off. I don't know how long I've had, to be honest. I think I've probably had the best part of an hour already, have I? Anyway, I'll keep going because you can go when you like. You can go make a cup of tea or whatever. I might as well keep going. Let's look at, we've now gone full circle because when we've got power electronics, we've also got the ability to create AC back from DC. And that's called inversion. And that's important because we can now start to use the fixed speed AC motor called an induction motor. There's a cutaway picture of one. Very simple rotor, doesn't have any sliding contacts or anything. In fact, no electrical connections to it are made at all. The currents in the rotor are induced. And it's very, very simple, but it only goes at constant speed, and that has been its disadvantage. They're not all small. That's a I don't know, 2 or 3 kilowatt one. Here's an 80,000 kilowatt one, 100,000 horsepower, with a couple of little ones at the top to provide cooling. Cooling has these things up here. So that's just to show the huge range. The major problem with the induction, see here, it only runs at a fixed speed. Well, having said that, you do have a choice of speeds, as shown there, 3,000, 1,500, whatever. But there's no way you could run it by just connecting it to the Yorkshire electricity and give you an in-between speed. The only way you could provide efficient speed control is if you can create a variable frequency supply. Well, it's no good bringing up the national grid and saying, oh, I want to go a bit slower. Can you slow down from 3,000 to 2,000 revs per minute for all your generators? No, of course not. We have to be able to create an AC. And that became possible when we got power transistors. You all know about the impact of transistors.
Hello. No, you can't really come up at the moment.
I'll keep talking because you get some interesting additions when you're doing Zoom, I think. Now let's look at the principle of how we create it, and we'll do it by a circuit with simple mechanical switches. But of course, those switches won't be mechanical switches when we've got it running. They'll be transistor switches. How do we get?
Careful, you'll knock the whole thing down.
How do we get an AC supply? Well, we assume we've got DC supply. Well, that in fact will have come from the AC supply having been rectified in the way we've seen. And then it'll be fed in on the left here. There's our incoming supply, the DC voltage, and there's the load that we want to have an AC on. So we'll start by closing a couple of switches, the one at the top left and the one at the bottom right. That means that the voltage, the load, if you look at the left-hand side of the load, it's connected to the plus V, and the right-hand side is connected to the naught. So the voltage it sees, for as long as we leave the switches like that, is a positive voltage. Then we'll open, I think, the top left switch and close the bottom left switch. Well, now the load, the two ends of the load are connected through switches to the bottom rail, so there's no active voltage between them. They're short-circuited together. And you can perhaps begin to get the idea. If we do another switch change, I've now connected the load so that terminal A goes to the negative and B goes to the positive, and then we can time however long we want these switches to be closed, and we can generate this sort of affair. Now, I said earlier, it's not going to be good quality AC, but it's alternately positive and negative. And for most purposes, we'll be interested in the so-called fundamental component of it. So it's a reasonable approximation to that sine wave. And the beauty of this circuit is that if we alter the time for which we have the positive and negative voltage applied, we can vary the frequency. So the lower waveform is a much higher frequency than the upper waveform. And if our induction motor is fed with a waveform like this, it's very tolerant and it's perfectly happy to run on squarish looking waveforms, and the speed will be proportional to the frequency. So we have a way of controlling the speed of what was for 100 years. In fact, Tesla, who we spoke of earlier, he is credited with inventing the induction motor. It's freed from its constant speed constraint. Now, I mentioned already we don't use a mechanical switch. We have a solid state device, a transistor. I'm not going to go into detail, of course, but it's a transistor. If you think where the name came from, it's a variable resistor. Trans means changing, and resistor gives the ist of it. It's a variable resistor. A transistor is a resistor whose value depends on a current fed into its control terminal. You can see there are two big heavy-duty terminals, and that's where the main current flows. And there's a little one, it's a bit like a thyristor. By choosing the current that goes in through the small terminal called the base, you can alter the resistance between the other two terminals. And in power operation, indeed, frankly, almost every transistor now operates either turn fully on, which is what we mean. By that we mean it has virtually no resistance between its two main terminals. So that's between this terminal here and this, where is it? There. And that depends on the current fed in to this terminal. So we can switch it from on to off, either make it look like a switch that's on or off. So instead of those mechanical switches, substitute transistors. The transistor is, of course, a solid state device. It doesn't have any moving parts. Here's some pictures of transistors, ranging from the one on the right could control a 200-watt load, and the one on the left very much smaller. And these will be combined not in 4 devices with 4. In most cases, we will need three-phase output, so we have to have 6 devices. The transistors are these things here, and these are the diodes, and you need 6 of them to create an artificial 3-phase variable frequency supply system. These things are available readily packaged. You don't have to wire them all up separately. There's a block, that's 2. And notice the size, that's the 6-inch rule. And those transistors are capable of switching a 3,300 volt supply carrying 1,200 amps. So, you know, when you think of transistor, probably most people think of a dinky little thing. But these are big boys, and they're real handling the power. We saw that we could create these artificial sine waves. There we are. But the perceptive amongst you will have said, yeah, but what about if you want to vary the voltage? Do you have to vary the voltage? Well, yes, you do actually. To make an induction motor run properly, you have to make the voltage go up as the frequency goes up, or conversely go down as the frequency goes down. And the way that's done is by saying, well, we've got this switching circuit. Why don't we switch on and off during the half cycle? And you'll see at the top, we've got a lowish fundamental component shown by the red line. And we've increased that in the bottom one by widening the on pulses during the positive half cycle. And that's called pulse width modulation. It's almost universal now, but it was totally unthinkable when I was a student. There was no way we could contemplate doing that at power levels. You might be able to play around with it with a hi-fi system, but not for real power levels. So it's really astonishing. It's interesting when you look at what you get on an oscilloscope. Those voltage waveforms at the top, they're supposed to be the best we can do to make a sinusoidal AC waveform. It looks pretty awful, but actually the induction motor is such a tolerant beastie that the current, which is the lower waveform, as you can see, looks a lot more sinusoidally. It filters out most of the high frequency nonsense, but they're still pretty awful waveforms, and doing measurements and so on is horrendous. Well, that shows that we can now get power from the fixed frequency system, rectify it, convert it back to AC at any voltage or frequency. Well, frankly, Edison and Tesla would have been astonished and delighted. And the sort of thing packaged now, that's for the one I use on my lathe, that's a picture of it. The inverter is this thing, variable frequency inverter down on the left here. Oh, what am I doing? I'm doing the wrong. No, I'm not able to get it to work. I don't know what's gone wrong, but it's down on the left, the induction motor at the back, and just the knobs to turn on and dial the frequency on the right. You will have seen, perhaps, if you're a camper, inverters like this. There's a set of inverters that allow the DC from the 12-volt battery to be produced and inverted to 240 volt 50 hertz. And those particular ones go in size from a 200 watt at the top to a 1 kilowatt for boating and so on. You can pay a bit more and get most of the ugly harmonics out of it and get a nice pure sine wave, but for most purposes you don't need to do that. The other extreme from those little things is the final development, which is that we can now use inverters to go from one AC system to another via DC. Now you may say, well, why do you have to do that? You can't just connect two large AC systems together unless they're exactly in phase, in amplitude and frequency. So if we want to send power to France, or more likely get power from France, it's impossible for us to join directly with wires because they won't be in step with us. The most horrendous beating would take place. But it is possible to take our three-phase AC, produce DC, send it across the channel as DC, and at their end, convert it back to 50 hertz at the right phase to connect to their network. And so here is a picture that shows you the links we've got at the moment. So we've gone from a 1 kilowatt camping setup with an inverter, and now we're using a rectifier and inverter to connect to France. You can see on the pink link, that was 160 megawatt, and they were Mercury Arc from 1961. And next to it is 2 gigawatt, 2000 megawatt, 2 million kilowatt. Hang on, yes, 2 million kilowatt. 1986 thyristor link, and these of course are very much bigger than the little boxes we saw. Here's a picture of the one, of one. This is a Canadian one actually. It turns out actually that for transmitting power over very long distances, originally AC was the winner, but there are problems with it. And now that we can produce very high voltage DC, it turns out that for very long distance links, it's best to convert from AC to DC and then back to AC again. And you can see some sense of the size of these installations here. And the towers, of course, only have one arm with two wires. Well, there are two circuits there. So we would find a rather different looking setup there. Nearer to home, I'm nearly finished. If you were to have been traveling on the Italy trains for 60 years. In 1959, the train would have had a DC motor with a Mercury Arc converter and non-regenerative, i.e. it could not return its coasting energy to the grid supply. Whereas in 2001, class 330s, I can't remember, 333 are they? They have AC motors, variable frequency. You hear the whine actually, the change in frequency as they speed up, and they have thyristors to rectify the AC and then convert it back to they rectify the AC from the 25,000 volt overhead and single phase, convert it to DC, then convert it in a transistor inverter to three-phase AC for the induction motors. And that combination can work backwards, so the train doesn't need the brakes much to slow down, it just regenerates its kinetic energy onto the supply. So I was going to finish there, and then I remember that sometimes, and I've only got 2 more minutes I think, people say, well, how did you get into electrical engineering? So I'm going to finish just by relating how, a paradox, how you get involved in things. It isn't always an obvious thing. When I was a child of about 8 or 9, my dad, on one Sunday after lunch, he gave me some bits to experiment with. He gave me a battery. He used to work, he was in charge of an airfield in the war, and he must have scrounged these things, an old Forces battery, some bulb holders like that. A thing I didn't know what it was a brass block with a thing in the middle of it. He gave me some coils of wire like that, and a penknife. And the challenge was, he said, I want you to arrange it that the bulb could be turned on or off easily. In other words, he wanted me to connect it up so it worked to work the bulb. Now I've got to move my screen a bit because it's gone crazy. Oh, there we are. Well, you can see I knew that the batteries were used for electricity, and I knew table lamps had wires to plug them in, and I knew the bulbs were the same as in my little bedside torch. I had no idea what the thing with the 2 blocks of brass and a tapered brass plug was. And that was, of course, I know now, was the switch. Well, I messed around with this all afternoon, and by tea time, with the help of concerning the removal of the cotton from the wires, I got the bulb to light up, but not with the switch, and I had succeeded in flattening the battery by short-circuiting it. So I'd failed dismally. And it was that caused me to pursue a career in electrical engineering, because when the solution was pointed out to me, I thought, actually, this is a delight, and I'd like to know more about it. And the solution that was presented to me was this, of course. I should have realized that the brass thing with the plug was a switch. And what I should have done was this. And the light came on, and that's the end. Thank you very much, and I'm sorry if I've seriously overrun, but never mind, some will still be there.
Thank you very much, Austin. Quite detailed, because I used to work for the electricity board and an electrical engineer like yourself, so it was quite fascinating to listen. And nobody seemed to fall asleep, because I went around everybody, and everybody's still there. So thank you. Just a couple of questions. Why are there different voltages around the world? In the domestic scene, we've got 240 volts, or perhaps 230. Over in America, it's only 110 or 120. So why are somebody's asking the question, why are there different voltages in the domestic?
Oh, yeah, well, you're the man to answer that, really, but the obvious answer is safety, isn't it? If you work on a building site here, you'll find that the electrical tools are required to be at 110 volts, not 240, because 240 will kill you, 110 probably won't.
No, but you'll enjoy grabbing hold of it. It gives you a nice tickle.
No, it's not pleasant, but it's a great deal safer.
Okay. The other question I've got is, what kind of electricity are solar panels, and how does the energy get to the grid?
The solar panels produce DC voltages, constant steady voltage. Oh, I don't know what's happened. Can you still? Oh, I don't know if you can hear me.
Yeah, we can hear you, yeah.
Okay. Well, something's happened here, but I'll continue as best I can.
No,
the solar panels produce DC voltage, not very high voltage per cell, but they're combined in series to produce a reasonably high voltage, maybe tens or hundreds of volts, which is then fed into an inverter to turn it into AC, which is then put into a transformer to produce the right voltage to connect to the grid system. And nowadays it looks perfectly simple. When I was a student, it would have been thought totally impossible. So it's really a delight. It's not a difficult thing to do.
Okay. Well, thanks very much, Austin. And I know we've messed you around slightly. We've had to rearrange the diary one way or another, but you've landed and you've been the first person on Zoom, so you can put that on your next CV. Okay, so thanks very much. Now, people want to applaud.
Yeah, thank you, Austin.
Thank you.